Yesterday we talked about the time loop. Time loop. Uh, as you see here, like I have two projects. Wait. Here you can see there are two projects, right? So yesterday I explained about this one. So you put the file, you put your VI file below the target. So suppose that if you want to make a new file running on the FPGA, you create a new file, you click on this target and then right click new VI. So it will goes down here. Okay? This is on the FPGA level. If you want to download it into a real-time target, you right click on the real-time and then you new click right click and then VI. It will write on the real-time target. Okay? So in real target you don't need to compile to FPGA. So, but however, for the FPGA, this one it will be compiled first to FPGA code. So it means that you need to be careful when you write this code because it takes some time to compile. Okay, so now let's go. So then, if you want to make a VI below your host, your PC host, you can right click on this one. So now this is running on your computer. It will not be downloaded to the real time, as I think. Yes, yeah, I think we can also get the, I think, like hard, hard limit and soft limit, hard time and soft limit. No, 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 not neural network. Like we need when we say that, even Windows we can use the CPU, right? Well, I mean, we can use Windows. So for here, okay, I will make example. Now, new VI. Yes, but still we can get the time loop here. We can specify the time, 1 kilohertz. Okay, the sampling time. How long do we need for one loop, right? But this is not hard limit, hard time, because this is being managed by the OS. Yes, but if we use this real time, then only the loop there. Okay. Yes. But I mean that it's more real time. But anyway, I'm not really also clear enough about this. Okay, let's continue. So let's go to the main. Okay, now I will explain the program for the excavator. Okay, this is not used. This is just my testing. Okay, only this program, main program. Okay, as you can see, what we need, uh, that we want to make a 4 degree of freedoms, right? 4 degree of freedom excavator. We show you the picture. See, this is 4 degree of freedoms. one one we call it swing, and then this one we call it boom. Actually, this one is actuated by this one. This is the cylinder, the hydraulic cylinder, and then after that, the stick is controlled by this hydraulic. So this is the angle that we uh, measuring, the joint that we're controlling, and then last one is the bucket. Okay, so there are four degree of freedoms. Uh, Last time we tried to use the on-off control. On-off control means that when it's on, it's moving, and off is not moving. Okay, so we thought that by changing the time of on and off, we can use PWM. We can use PWM. However, when we finish uh, when we finish using the ATmega and programming, we found out that the the valve doesn't have fast response. So if we give 50 hertz, 50 hertz. Okay, I will explain. 50 hertz means that 20 milliseconds, right? How to call it? You know how to, right? It's very easy. 1000 divided by 50, 20 millisecond, 0.02 second. It means that it means that uh, one duty cycle is 20 millisecond. One period, the on and off ratio. This to this. Okay, between this, we call it 20 millisecond. Okay, 50 hertz. So it's suppose that we have 50%, 50% on, means that this is 50%, right? This is last is 50%. Yes, the speed become 50. If we say that the duty cycle is 30%, then yes, right, 70 and then 30. But still, that the one period is 50 hertz. Why we choose 50 hertz? Why usually why 50 hertz? Why? Yes, yes, yes. That's right. We can call it like bandwidth. Bandwidth. Uh, yeah, working bandwidth. So suppose that if we give too much frequency, the actuator cannot catch up the speed, the updating speed. So we need to use a small one. So in this case, as you can see, we create, we can choose. Okay. I actually we can more than this, like 1 kilohertz, but it's not possible for the. Okay. However, in the actuator itself, actually it doesn't mean anything 50 hertz because it's the same. Because the valve is very bad, not good condition. So it means that if you give 50 hertz and 10 hertz, it's the same. Yes. What I mean that yes, maybe yes. So You know, in our system we have three modes, right? Joint control, yes. So hybrid mode and then task space mode and effector mode. However, we can in this case we cannot use the effector mode because we only by valve to valve. So here, okay, here's the problem. Because of we cannot control the speed, you know, we cannot change the PWM. We cannot change the speed, right? We cannot change the speed. We cannot do the n factor control, robotics control, right? So we change that on the swing and on the bucket. We need only the PWM. We can use the PWM. However, for the boom and for the stick, we change using the proportional control, the AC. Yes, analog, minus 10 to 10 volt. So it means that we will need two PWM and two DACs, right? Okay, so our program should contains both four of it. PWM, two, DACs, two. Understand? Okay, any question until this? Okay, good. So and then now, what are the inputs? Yes, joystick and push button. So, okay, the real implementation that we can only apply the joint control, and second one is the hybrid control. And hybrid control is not possible. Yes, why? Why? Yeah, yeah. When I mean that we can control the swing, right? Because we only have the AC too. We only have two DACs. Yes, so the swing cannot be controlled. So it's not possible. We can only have hybrid control. So the input are push buttons, 8. Why we need 8? Why not 4? Yes, from the name you can see, right? Positive and negative. Yes, we need push button 8 because there are 4 degree of freedoms. Means that 4 divided by 2 is 8 for joint control. Joint control. Not task space. Task space only X, Y, Z, right? No, no, only Y and Z. Y positive. Okay, I just forget it. Okay, just keep it like later. So we have this one. Now you can see button and joystick, and then also and then we can switch from open loop and closed loop. Open loop means that only joint control. Closed loop hybrid control. Yes, we use PID. So what we need? What we need are input and output. Okay. We need two DAC, two PWM, 8 input push button DIO, and then we need joystick. We use joystick, two joysticks. Two joysticks, one joystick is able for 2 axes. So means that two joysticks, 4 axes. How many channels do we need? 4 channels, the ADC. 4 channel ADC, and then we need the feedback, right? The feedback, you know, the feedback from this, as you can see here, from the we will put LVDT. You know LVDT? No, like ADC. It's like a displacement. If it's retract and retract and yes, but it's linear. Potential is not linear, right? No. I mean, what is the curve? The curve linear? Yes. Wait, I don't know about characteristic. Anyway, this is very precise. This should be precise. So it will be put here. If it is retract, the voltage is changing. If it is what is called retract and then contract, yeah, me extend. It will if we extend, then the voltage also is also changing. So how many feedback do we need? Yeah, only two. Yes. However, I think we will need also for the bucket. So we just remove the swing. You know we have for the AC for ADC, right? For the joystick, one for the boom, one for the and then the other one. Okay, for the axis, one for the boom, five, and then one for the stick, six, right? Six ADC. Okay, you understand? Okay, four. Yeah, we need to control the boom and the stick, right? For the velocity control. How can we get the feedback? This is closed loop control. No, ADC. Oh yeah, what I mean that the ADC, the AC is the actuator, right? So we need one and two. So how many now? Six. So because we have eight ADC channel, so one I'm using for the bucket. So I'm planning the bucket, like this automatic. Look at my hand. So how about if we generate trajectory to automatically do this? Yes. No, what I mean that the bucket only the you can use like open loop. No, I mean that open loop, but with the you don't need to control the velocity, but only the position. You understand? Just this plan. So I just put one reserve here. Okay, so we have seven, right? Last one is for the velocity. So there's here, potential here. We can change this potential. We can change the speed by changing. We can change the speed by changing the potentiometer. So we okay now we I understand. So we have eight ADC. Okay, can you repeat then? Yes, yes. Okay, now we have eight ADC and then two DAC and then uh mm, two no four PWM, right? Four channel. Okay, I will explain about the PWM. The valve is controlled independently. You understand? Suppose like you have only one even here. You see the swing, for example, swing. If you want to move it to the right side, right, there's another input. Yes, it's different. So we need to the PWM. So we should never use both at the same time. I don't know what happened. Yes, for the AC is only one, right? Because negative and plus. But this is no. So we need, you understand? So we need four channels for the PWM. Okay, I will repeat. 8 channel for the ADC, to the AC for the IO digital output. Because PWM, I will show you the program later. For 4 for the outputs, and then 8 for inputs for the push button, right? And then one digital input for the mode. You know the mode? Yes, join to hybrid. Yes, actually one button more, but I didn't implement it. One button more for the choosing whether using button or joystick, but I did not implement it. You understand? So okay, now this is the high level one. Okay, this program, this program will call this program will call the you need you see this actually here you see here. Where's the okay? I want you must be curious, right? Where's the FPGA program? Yes, right. How? You must. Where's the FPGA code? Where's the FPGA code? See? Yeah. No, actually, this is called by reference. What I mean that he called actually this one called the reference. He called the FPGA. Okay, if you click on this one, yes. Actually, no. Right click and select um, here. Right. See on this one, it is below the FPGA, so you can choose the main program. When you okay, when we choose the main program, you can check. You can get this one. Yes. See how from where this one? This is from the FPGA. Yes, the variables. The okay, we will go. Okay, please take a look at this one. So I will open the FPGA code now. This is the FPGA. So as you can see here, we need what do we need? We need PWM, right? This is PWM for the bucket and for the swing. For the bucket and for the swing, and then we also need 8 button, right? In 8 buttons. Uh, Here I use the this one because yes. Why? Yes, because please don't forget that don't forget that this only support Actify. I don't know how to change it this model. So if you I don't know if you make your system, you should please think before that. Yeah, I think it's better to have Actify. No, no, I don't know why. And this is the AC because the AC we are using the calibrated. So we just put the voltage. This is voltage. This is very directly. So if we enable the DAC, it will throw. Okay, throw and then go. If it is false, then zero volt. This is the easiest one. Push button. Okay. This is the ADC. I'm using the Butterworth filter on the FPGA level. One. This is a real time FPGA. Here we can choose the yes count of frequency and the sampling rate. So I will pass the data below 250 hertz. If you increase this one, noisy, yes, will start to appear. Okay, and then you see here all okay, and then you see here that all the on each loop there's stop button, right? Yeah, stop button, stop button, stop button. You see all this is same, but only one. So how did I do this? So you make call local variable. You right click on this, create local variable. Now it becomes, see, same. You can change to read, only read mode now. See, same, right? So yes. Any questions until this one? Okay, now the PWM. I think you can see the flow is not difficult. What we want that this is one tick, right? We have to do calculation on this one. Okay. At first, one tick is 25 nanosecond. 140, 1 per 40 megahertz is equal with 25 nanosecond. Okay, at the beginning, it is true. At the beginning, it is true. The and then this is ticks of the swing PWM high time. Okay. Oh no no. Oh wait. Oh yeah, yes yes. Wait wait. Okay okay. No no not this one. Okay, at the beginning, you see you have the period, right? PWM period hertz. Here in this one, see 100 hertz, 40,000. 1 hertz, 40 million. Okay, it means that when you run, wait, I don't want to change. Okay, it means that if we give, this one is the hertz, right? You saw right? If it is 1 hertz, 40 million, right? 40 million times tick. Okay, just the value. Just forget the value. It means that if you run 40 million times, this loop runs 40 million times, or 50 million, 40 million tick. How? What is the time? Okay. Yes, right. 1 second, right? Here 25. Okay. You know, we have 40 megahertz. 1 divided by 40, right? 25 in a second. We want to run this on 40 million. 1 second, right? So you are right. 1 hertz, 1 second. You understand? So in this program, if we give this value, please pay attention. Suppose we give this value is 20 million. Wait, please wait. 20 million. This is 40 million. Okay. At the first beginning, it run on this one, run true. Whether true or false. Okay, no problem. Okay, maybe false. Or maybe false. Uh, False, right? This is 0, and this is 0. Okay, 0 is higher than 0. No, right? False. If it is false, then it is false. Means what? Low, right? Means low, right? This is low. Understand? Okay, it's low, and then so if it is low, it means that DIO1, I think this is negative access. Oh no, if it is false, if it is okay, oh no, if it is false, this is false, right? If we enable DPWM, you understand? When both are false, you understand? It means that uh, false, true, false. It means false, right? So 0. There's no voltage on the output. Okay, false, and then goes here. The loop goes back. Okay, loop goes back. Now the tick become 1, right? We add +1. Here is plus, you know, I plus plus, +1 increment. So it will increment the period count, increment, and then it check equal or not. So if it is equal with 40 million, this is 40 million, right? Then it will start from 0. Start again from the beginning. But so it's still not 40 million, right? Still number 1, still 1. If it is false, okay, if it is false, then this one goes to false. Okay, goes to false, this is false, goes to false, and this still how much? 20 million. You understand? No? I will repeat. Okay, I will repeat from beginning. Okay, please don't forget. This is 20 million. This is 40 million. You want to do 50%, right? So at the beginning, this is 20 million goes here. Okay, 20 million goes out. This is 0. Check. If I think I was wrong previously. 20 million is bigger than 0. Yes, true. If it is true, we goes here. True. So it means that if it is true, this is true, right? So DIO1 is true, and DIO0 is false. So this is the IO 1. This is the IO 2. This is the IO 1. Okay, understand? Okay, go and then the loop returns back to the beginning. This is incremented, right? 0 plus 1, now it becomes 1. 1 is equal with 40 million? No, because it is false, then it's 1. Okay, goes back here. Okay, this will always it will be incremented all over and over again until this reach 20 million. 20 million and 1. Now it checks bigger or not. Bigger. No, false, no, false. This is 20 million and 1. This is 20 million. False, right? This goes to false. Yes, false. No, both are 0. Mm, see? Now becomes 0. But this is still 0 because okay. We choose the swing positive manually. You understand? Yes. Yes. If it is positive, then if it is positive, then this is the positive axis, right? If it is negative, false, false, then negative, then this is the output, PWM output, DIO 0. So this swing positive and negative is on the higher program, the RT, as we can see here. I use XOR SOR logical because cannot but at the same time it's not allowed. You understand? Because the as I explained before, the false is controlled independently, right? If you want to go to the right, you use one output. If you want to go to the left, you use another one. What happens if you give both? Maybe it's shaking or maybe it can blow out. I don't know. So you have to SOR. I SOR. One and one is not possible. So only one at the same time. Only one is allowed. Okay, so this one. This logic why I use this. Please don't forget that. Okay.